Will the universe die, and when? What are your estimations?
That is an enormous question, and yeah, I already like this session because we're diving into not small things. Imagine if you and I right here, we took a horse and we magically inflated the horse to the size of the known observable universe in the same amount of time, 10 to the power minus 35 seconds.
Poor horse.
Yeah, I know, poor guy. Physicists back in the 90s, they were like, oh yeah, the universe is one sort of thing, and it's kind of expanding at a kind of constant rate, and da-da-da-da-da. This is completely wrong. And tidal gravitational forces will shred the charred Earth into dust, which will slowly sprinkle toward this tiny, dense, dark sun and be absorbed. And that'll be the end of the Earth.
We're made of stars?
Yes, we are. Yes, we're made of star stuff. We're made of stardust. We know for a fact that dark matter exists because we see its effects on the cosmos due to gravity. And if it's not light stuff, then it's dark stuff, therefore dark matter. So dark does not mean mysterious. It doesn't mean evil. In fact, 68% of all of the stuff budget in the universe is made up of this stuff called dark energy. It's possible that just a brain will appear out of nowhere.
And
or
what will it do? I mean, like sad, lonely brain sitting somewhere,
Yep.
I don't know, floating through the universe, and he's like,
Yep.
who created me?
Yep.
Is there a God out there?
Hey everyone, that's Renegade Science podcast and your host, Marie-Énie Puer. In this podcast, I meet scientists and entrepreneurs that are working on groundbreaking technologies that will eventually change our world. I talk to them about their work and areas of expertise and ask all the burning and stupid questions, the most important of which is, how do we build a great future powered by tech? Don't forget to subscribe to our YouTube channel and social media. My guest today is particle physicist at the Large Hadron Collider at CERN, data scientist, filmmaker, speaker, and an amazing storyteller, James Beacham. He hunts for dark matter, gravitons, quantum black holes, and dark photons as a member of the Atlas collaboration, one of the teams that discovered the Higgs boson in 2012. James will blow your mind and you will fall in love with physics even if you always hated it. Let's go.
Hi, James.
Hello.
Thank you for being here today.
It's my pleasure. Thanks for having me.
So, after this beautiful prelude about multiverses, I would love to talk about another fascinating topic, which is universe started at some point and it will end. So is it true? Will the universe die, and when? What are your estimations?
That is an enormous question, and yeah, I already like this session because we're diving into not small things. We're diving into the biggest possible question. What's the eventual fate of everything?
42.
you can't get bigger than that, right? I like it. I like podcasts that go big. So it's an interesting question because once again, we as humans, we are extremely limited, right? There's just, we as humans, we're stuck on this rock, this very kind of friendly, special rock in this kind of weird, sort of normal looking, not even weird, just sort of normal galaxy in this normal cluster of galaxies in this weird corner of the universe. So there's really no reason for us to think that we should have special insight into this. But it's actually quite remarkable that we can use the tenets of science and we can use what we know about, physics and astronomy and all these kinds of things to arrive and make some measurements and to arrive at an actual idea, a real scientifically motivated idea as to what the final eventual fate of the universe could be. And that's amazing if you think about it. 1,000 years ago, people would make up stories about, thousands of years ago, they would make up stories about where the universe came from, what's going to be the eventual fate of everything, because they didn't really have any better, explanation. They didn't have any, well-developed scientific methodology to make any kind of concrete predictions, and so they would make up stories and narratives that made sense at the time. Now we have slightly better idea. We have better techniques that are more robust and repeatable. So The short answer is that quite probably the universe will end in the so-called heat death of the universe. And this is a state of everything in the universe where basically nothing can ever happen ever again. What it is that what we know, let's talk about what we know. What we know right now is that our universe is about 13.8 billion years old. And about 13.8 billion years ago, the universe started from something very small. We don't actually know what happened at t=0. In fact, there might not even be a t=0. There's a kind of, it has to do with the uncertainties built into our understanding of the universe at the quantum mechanical level. There might not even be a t=0. It might, like the question, what happened before the Big Bang, might not even be a well-posed one. Anyway, so the universe started something very small and started to expand. And we know that it's still expanding today. However, the universe did not just expand at a constant rate. It went through 3 different so-called epochs or epochs of expansion. At first, when it first started to expand, it did something called inflation. So it went pow, and then it slowed down, and it went like that for a very long time. And then it started to speed up its acceleration. So it's very, very weird. It's strange that we can even...
What happens?
Yeah, that's a very good question. You're asking the key questions. Yeah, so... And to give you a sense as to how strange the fact that this expansion happened in 3 different bursts, if you will, this initial inflation happened so quickly, like so much faster even than the speed of light that we can't even wrap our brains around it. So it went from something infinitesimally small to something about the size of, I think, a soccer ball or a football. You know, I'm talking to the American audience here. From something from extremely small to something about the size of a football, in 10 to the power minus 39 seconds, I think, or minus 35 seconds. So that, and to give you a sense as to that scale, imagine if you and I right here, we took a horse and we magically inflated the horse to the size of the known observable universe in the same amount of time, 10 to the power minus 35 seconds.
Poor horse.
Yeah, I know, poor guy. But that's what inflation was like back at the moment of the Big Bang. So the universe did that. But the weird part is that then it stopped. We don't actually know why this happened, but inflation stopped. And it was very weird. So it went pow, and then it kind of slowed down. And it went that way. And it was still expanding, but it expanded at a much more gradual rate for about 10 billion years. And then about 3 or 4 billion years ago from now, in the past, something turned on in the universe that started to force the fabric of space itself to start to accelerate its expansion. And so this has been going on for the last few billion years, and it's still going on now. And this was a total surprise. This happened in the late 1990s. In fact, you think about it like as a physicist, even in our lifetimes, right? Physicists back in the 90s, they were like, oh yeah, the universe is one sort of thing, and it's kind of expanded at a kind of constant rate, and da-da-da-da-da. This is completely wrong. In 1998, a bunch of some observational astronomers, they're like, guys, we have a very interesting observation here. It turns out that the universe is not just expanding, it's in fact speeding up its expansion, like it's accelerating its expansion, and it seems like it's going to do that forever. So that happened in the 1990s, completely changed everything we knew about the expansion of the universe. But it also had some very interesting consequences, which is related to the question you're asking, right? Is that the first thing you ask yourself is like, okay, wait a minute. What does this mean for the eventual fate of the universe? Yeah, before 1998, before the late 90s, physicists were like, well, probably what's going to happen is that even though, things we had the Big Bang and inflation and things started to move apart, in nature, in the universe, everything in the universe, everywhere, at every possible scale, there's always a fight going on between different types of forces. Right? So for example, you and me sitting right here on this sofa.
And we're fighting for the sofa.
Exactly, fighting for the sofa. No, but physically, if you were to zoom in to the atoms right in the very bottom of my foot, and the atoms on the rug here on the floor, in fact, if you were to zoom in on that, there's a fight going on because gravity wants to pull me toward the center of the Earth, right? So one force is pulling me that way. However, if you zoom in, there's in fact something called electrostatic repulsion between the electrons in the floor and the electrons in my shoe, and also something called Pauli pressure, which is a quantum mechanical effect. Anyway, those are fighting against gravity. So there's always a fight going on. It's also the same in the sun, right? You have, gravity wants to pull everything in the sun toward the center, but then you have this fusion power that's pushing everything out. There's always a fight going on all the place. There's also a fight going on in the entire universe, right? Because if we had expansion, that means that, something at the moment of the Big Bang flung everything into all directions. It kind of went pow, there wasn't actually a sound. The word Big Bang is just it's a kind of a poetic thing. There was no bang, there was no sound.
Because it's space.
Exactly.
No sound in the space.
Exactly. Kubrick got it right. There's no space, there's no sound in space. But this expansion started to happen, but then you might think, okay, this expansion happened, it sort of like flung everything out, but you might think, okay, there's a fight going on because everything in the universe also wants to attract each other because of gravity, right? I mean, we know that's the case. The Earth is sitting here and the moon is sort of falling around the Earth in a constant orbit. That's what gravity is, right? It's sort of like gravity arises because, the presence of stuff within a certain volume of space creates a kind of sinkhole in space itself. So the moon is sort of falling toward the Earth at all times, right? This is also the case on large scales too. So you might think that, even though this expansion was happening, eventually some physicists thought in the 90s, they're like, okay, eventually this is going to slow down because all this stuff, gravitational attraction of the stuff, will pull it toward each other. And so eventually the final fate of the universe may in fact be a so-called big crunch, right? 1998 then happened and people thought, oh, damn. Okay, so everything is in fact accelerating its expansion, and then you can measure very precisely how much of this expansion is happening, this acceleration is happening, what rate of acceleration it is, and you can then kind of balance this against what the assumed gravitational pull should be, not the assumed, but what the measured gravitational pull should be toward these things, and you can then arrive at the conclusion that, as far as we understand now, this expansion will continue to happen forever. And it will never slow down. It will continue to accelerate. Yes.
So will the universe become a collider at some point?
I don't know. I don't think it's going to necessarily be a collider because at some point, if you go far enough into the future, everything will probably disintegrate. Even the particles around us will probably disintegrate, and you'll be left with probably some photons and some neutrinos.
How about the law of the conservation of energy?
Well, that's a good question, right? And law of conservation of energy on the universal scale, it will still be satisfied because you also have to think about the laws of conservation of energy, but you also have to think about the laws of entropy too, the laws of thermodynamics, right? So related to this is that the eventual fate of the universe, right, will be something, again, if we have a constant expansion or a continued accelerated expansion, does this mean that eventually there will be something like it will go too fast and maybe it'll be, space itself, exactly, like a big rip, which you've probably heard about, right? Yeah, so will that eventually happen? You can also, but then you can measure this. For example, there's other things that we can measure about the expansion rate of the universe and about the vacuum expectation values and all these kinds of things. And you can put these together. And as far as we can measure, it will probably not big rip. It will just continue to be sort of like a flat, so to speak, a flat acceleration, which gets a bit weird in terms of its terminology for those people that are not physicists. But suffice to say that if it does this kind of flat-ish acceleration forever, eventually the universe will turn into just this kind of completely empty soup of nothing. And and we're talking, you mentioned the time scales too, right? So, when will this happen?
Yes.
Okay, so, we know that from right now, in about 6 billion years from now, the sun will expand just enough to engulf both Mercury and Venus. They'll be vaporized. The Earth, however, will probably just barely survive as an object, except the sun will be so large that it'll just burn the Earth to a crisp. And this charred clump of coal will orbit the sun for an extremely long time, during which the sun will change from a red giant to it'll collapse to something called a small white dwarf, and then eventually it'll give up anything that can give off radiation, and it'll turn into a black dwarf. And our crispy ashen chunk of Earth will slowly orbit closer and closer to the black dwarf sun until about 100 million billion years from now, tidal gravitational forces will shred the charred Earth into dust, which will slowly sprinkle toward this tiny, dense, dark sun and be absorbed. And that'll be the end of the Earth. The only home we humans have ever known, as Carl Sagan once said.
Yeah, but we died many episodes before, probably.
Probably, yes. However, of course, that's just the end of Earth. The universe will continue without us, of course. And eventually, though, they're open scientific questions right now. Eventually, all the stuff in the universe, big structure, will just kind of break apart, right? At some point, all the stars will give off all of their energy, and a lot of them will just do a supernova and then collapse. Some will collapse into black holes. Some will turn into neutron stars. Some will turn into little kind of dense objects. But eventually, over very long time scales, all this stuff probably will disintegrate. So one of the big open questions in science right now, it's such an enormous question that you probably would never even think to ask it, most people, is, I said earlier that we're all made of a bunch of protons and neutrons and electrons, but so focus on these protons.
We're made of stars?
Yes, we are. Yes, we're made of star stuff. We're made of stardust.
But that's true.
It is, we are. It's true. It's absolutely true. But these protons, they're all around us, and we've never, in an experiment, we've never seen a proton decay.
Die.
Yeah, we've never seen a proton die. This is very distinct from other things like it, right? We've seen neutrons die. In fact, when I take a neutron out of your one of the molecule or one of the atoms in your body, right, and I'll let the neutron hang around, it'll hang around for maybe 10, 15 minutes, and then it'll do a sort of decay process where, in fact, it spits off some stuff and then turns into a proton.
Yeah.
So we know that neutrons decay. We know that a lot of other particles decay. That's like my whole job, right? However, we've never seen a proton decay. So it's an open question that sometime in the very, very far future, do protons decay? Some people think they must because of various reasons. My theorist colleagues, they think, oh yeah, definitely protons will decay because of X, Y, Z. And some people say, no, there's no reason for that to be. Maybe they're continually stable. But it seems likely that at some point very far in the future, protons themselves will decay, which I think is something like, I forget when this is, 10 to the power 40 or 10 to the power 50 years from now. Don't quote me on that, but something extremely long from now. The current universe is only 10 to the power 10 years old. So this is very far into the future. But eventually, if that happens, eventually protons themselves will just decay, which means that basically everything else has to decay too. And you'll be left with, like I said, the particles that can't decay, which would be photons, which is light, and radiation, and then possibly neutrinos, which are these tiny, tiny ghost-like particles that are flowing through us all the time right now. So for example, anybody listening to this, next time you go outside and you see the sun, think of me and hold up your thumb to the sun. And when you hold up your thumb to the sun, you have about 60 billion particles called neutrinos passing through your thumb every second that are coming from the sun.
Wow.
So these are all around us. And as far as we know, they can't decay into anything. So they'll probably hang around. I'm just belaboring this point because at some point, very, very far in the future, there's basically nothing in the universe except for black holes. And black holes will dominate the universe for an extremely long time. But we also know black holes, eventually they must evaporate. You've probably heard of Hawking radiation. This is how black holes, we know they suck in stuff for a very long time. But over a very, very long time, they have to probably give up all the stuff that they sucked in. They have to eventually radiate this out again, evaporate. And even on extremely long time scales, black holes themselves will decay. We're talking 10 to the power 60 years from now, 10 to the power 100 years from now. And after that, black holes will dominate the universe until eventually all the black holes will evaporate. And eventually, in the end, in some unfathomably long time, like longer than our human minds can even comprehend, 10 to the power 1,000 years, 10 to the power 1,000 to the power 1,000 years. Like I can't even wrap my head around this. Eventually, our universe will probably reach a state of maximum entropy and nearly absolute zero temperature. Probably not absolute zero, but something nearly absolute zero temperature, which means that literally nothing can ever happen in the universe ever again, and will stay that way probably for eternity.
This is a miserable perspective, although we will be all dead by that.
Oh, we'll be so long dead that we will not even show up in any history books of the universe at all. Like the historians at that moment, 10 to the power 1,000 years from now, they won't even, we won't even be part of their memory at all. Okay, they won't exist either, but because their protons would have decayed. Yeah, it's a bit of a daunting thought, I guess. I don't know. Something about it to me is interesting. Well, not something. All of it is interesting scientifically, right? For example, and that would be amazing. Like, think about what that would be. Not just the heat death of the universe. That would be incredible, like, just to experience. But also, like, before then, think about, there's parts within that chronology we just skipped over, right? Imagine, we know that, for example, the universe is expanding. We know this expansion is accelerating. And we know that, sorry, go ahead.
We know that. Why? Because we observed, some light coming from many years from the past. This is why we know, that something happened, and with which speed this expansion goes.
Yeah. We know this because of, like you're saying, because of observational astronomy. Basically, my astronomer colleagues are very good at looking out into the sky and looking specifically at certain kinds of, mostly galaxies. Some stars are closer to us, of course, we can measure those things. But if you look at galaxies, we know that galaxies are made up of a certain amount of stuff, right? A certain kind of finite number of elements. There's not going to be any magic elements that are, in that part of the universe that are not here. It's one of the big assumptions that we make in physics and in astronomy that, we think is well motivated. Okay, maybe we can't experience everywhere in the universe. I can't suddenly go to Alpha Centauri to measure if things are different there. But we make the assumption that the universe is so-called homogeneous, right? There's no reason that the little patch of universe around us is something wildly different from, the stuff that makes it up is somehow completely different from the patch of universe that's around, Alpha Centauri or something like that. We make that assumption. But that's a good assumption because it allows us to say, okay, we know what the stars in our galaxy are made of, right? Because we know what our sun is made of. Our sun is nothing special. It's just one of a kind of normal, boring star. We see stars like it. We then say, okay, that star is like ours because we can measure from the light spectrum the kind of peaks of the different elements in there. And we say, okay, this is a kind of fingerprint of a certain kind of a star that has certain stuff in it. So therefore, if you see that fingerprint, this kind of pattern of this kind of spectrum of the different elements that you see, you can also see this fingerprint in other galaxies that are farther away. And so you say, okay, this galaxy that I can't look at it as closely as the ones that are close to us. I can also look at it and I can say, okay, this has the same fingerprint. It's just slightly stretched because if everything is moving apart from each other, the light that's coming from that galaxy is, and if it's moving faster and faster, it's going to be so-called redshifted. You've probably heard of the redshift, right? What this means is that the wavelength of the light, because the fabric of space in which this light wave is moving is being stretched, it means that its wavelengths overall will be stretched out as well. So when they get to us, they will be stretched out, except the same fingerprint pattern will be there. It's just maybe stretched out in a way. Does that make sense?
Yes.
So we can do this with basically all the galaxies. And we can look at this, both the ones that are closer and the ones that are farther away because the redshift is more, and the ones that are farther and farther away because the redshift is even more. And eventually, if you look out to the very, very edges of our universe, the edge of the observable universe, those galaxies are moving even farther apart at a much faster clip. So, and you can do this at all the kind of like ladder moments, right? It's like the ones close to us, the ones just a little bit farther away, the ones a little bit farther away, ones a little bit far away. Everything has the same signature. So that demonstrates conclusively that the universe is expanding. Everything in the universe is expanding away from everything else. And if you get the farther away you get from any given point, that stuff is moving farther away, and it's all speeding up as well. Does that make sense?
But how can we prove, as an example, we are sitting in the solar system, what actually happens is a big crunch, because we would observe the same thing. If we would be crunching faster and faster, we would still observe same acceleration.
You mean if space were in fact contracting instead?
Yes.
We'd see it the opposite instead. We'd see the other directions. Because if we in fact measured that all of the galaxies, if I understand you correctly, the galaxies were getting closer to us, we would see it so-called blue shifted. Because that's the way the light goes. And again, like I said, it's kind of weird to visualize in a way, but you can think of it like it's a kind of a Doppler shift. If you remember from sound, if you ever
Doppler effect.
Yeah, exactly. So, for example, if you're standing right here, and again, being in Berlin, we have here in Berlin some of the most unnecessarily loud ambulance sirens in the entire world. And so, if you're standing in a street corner, right, and then you hear the kind of suddenly this ambulance starts to go, and then as it's farther away from you, as it gets closer, you hear the pitch is shifted, and then as it goes away, it's a. That's because it's moving away from you. It's still locally. It's giving the same pattern that's coming out, the same frequency, except as it's moving away from you, the pattern is stretched out, and by the time it gets to your ear, it has a different wavelength. It's the same thing with light as well. So you remember from the Doppler shift, if it's far away from you, and then the ambulance is coming close to you, in fact, it'll go the other direction. Yes. And then as it goes away, it goes the other direction. So that's how we could distinguish between a so-called crunching universe and an expanding universe.
Oh, cool.
Yeah.
Yeah, now we understand. We are expanding.
We are, yeah. It seems that everything is expanding. It's also a very key thing to keep in mind is anytime you talk about the expansion of the universe and the Big Bang and inflation, the clever amongst us will then say, okay, I've heard these words before, but wait. When the universe started from something extremely small and it started to expand, what does that mean? Does it mean that the universe was expanding into something? Like when we say that the universe is expanding, what is it expanding into? Right? Is there something like outside?
Is there something outside the universe?
Yeah. Is there something outside the universe? Is our universe, for example, like a balloon inside of a box, right? And I'm blowing up the balloon and it's just blowing up inside the box? No. The universe is in fact just the balloon. There is no box. And
How do we know that?
Well, yeah, the question of what's outside the universe is not a well-formed question. There's an infinite number of not well-formed questions that we can ask, which is why in science we focus on the ones that are well-posed, well-formed questions. And the reason there's nothing outside of the universe, and we know that, is because it's not necessary. Because when we say those words, the universe is expanding, what we mean is that the fabric of space itself is being stretched. So there is nothing outside the balloon. The entire universe is on the surface of the balloon, in my metaphor. Yeah. So, again, which is weird because we think of space as a kind of nothingness, right? It's like space is not a thing, right? It's sort of it's like a background, idea. It's like a nothingness. It's like a void. It's like a background metric grid upon which we then put our ideas. That's not true. What we actually know is that space has a kind of stuffness to it. It's kind of like a rubber sheet. If you and I had like a rubber sheet and we're pulling it from all sides, that's kind of what space is like. And imagine I put 2 pins in the rubber sheet, and we start pulling on it. Mm-hmm. From the perspective of an ant on the sheet, nothing happened to make the pins start to move away from each other. But you and I are pulling on the sheet from all directions, and the distance between the sheets, between the pins, is moving. From the ant perspective, he's just like, okay, the 2 pins are moving away from me. Nothing happened, right? There's nothing like pushing he can't see us pulling the sheet. So that's what we talk about when we talk about, the universe is expanding. Keep in mind that there's nothing outside of the universe. The universe is everything that exists. And the fabric of space itself is being stretched. And then, of course, you might ask the question, stretched by what? How is this happening?
Of course, I want to know.
Well, that's the big open question. We don't know the answer to that. It's one of the big open questions of science right now is what is causing the accelerated expansion of the universe? What happened about 4 billion years ago to just bing, and then suddenly it started to expand and accelerate? I don't know. If you know, please tell the rest of us because there's a Nobel Prize waiting for you.
Perfect. Leave a comment to this video and tell us who causes the acceleration of the universe.
Yeah, well, we have some ideas, and a lot of people may have heard. It's related to this idea that a lot of people might know as dark energy. Yeah, which in fact is a completely different question, open question, than the question of dark matter. They both have the word dark attached to them. In the dark matter case, We know for a fact that dark matter exists because we see its effects on the cosmos due to gravity. We know that galaxies are spinning faster than they should. Therefore, there must be more stuff in galaxies than what we can see with our telescopes. And if it's not light stuff, then it's dark stuff, therefore dark matter. So dark does not mean mysterious. It doesn't mean evil. It just means it doesn't interact via light in the dark matter case. However, with dark energy, that kind of means we have no idea. It means that there's some amount of stuff in the universe. In fact, 68% of all of the stuff budget in the universe is made up of this stuff called dark energy. And this is the stuff that must necessarily be driving the expansion of the universe.
Because it has a weight?
Well, not that it has a weight, it's just that it has an effect that is equivalent to making something happen. Mm-hmm. Force and energy are related in physics, right? And so if you have something happening, something that's driving
it's like
this
energy
acceleration.
Potential.
Kind of like that, yeah.
Why I said weight, because if you have something heavy, and it's moving, so you have this inertia, this momentum that moves the thing forward.
Right.
So maybe dark energy has this potential or weight or whatever. But,
it has to, right? I mean, sorry, I didn't want to interrupt you. But you're right. That's exactly the thinking we have. Is like we observe one thing, that the universe is expanding and it's accelerating. The expansion of the universe is accelerating. Therefore, something must have caused this. It didn't happen for no reason. Again, back to the physics. What is the reason? What is physics? It's a search for mechanisms, the how and why physical phenomena occur. Not just throwing up our hands like, well, that's just the way it is. Instead, we look for mechanisms. And so people think, okay, something must be causing this. And it must be some kind of energy. Again, like you said, it could be some kind of, your metaphor of some kind of potential energy or some kind of stored energy, blah, blah, blah. It gets more complicated for the concept of expansion of the universe too, because in fact, it gets way more complicated. I don't know how much detail you want to go into here, but it's super weird. So there's two things going on. We see that we observe that the universe is expanding and accelerating its expansion. Like I said, something turned on a few billion years ago that is pushing this expansion of the universe. There's something else we observe about quantum mechanics. Okay, so we know that the rules of the universe at the smallest possible scale are governed by something called quantum mechanics, quantum field theory, but for our purposes, they're the same thing. And with quantum mechanics, it's super weird because with quantum mechanics, nothing is ever stationary. Even and I say that in a very, very key way, because even nothingness itself is not stationary. So if you zoom in on the fabric of space itself with nothing else around, eventually you'll get down to just little quantum fields. And in fact, this quantum field theoretical idea is fascinating because, you might think about that, if we get down to the smallest possible scale of everything, particles, right? This is what my field is. If we get down to the smallest possible things, like an electron, right? If I have an electron, you might imagine that the best way to describe this electron's movement in the universe is by, like a little chunk of something. I have mathematical equations for, like, if I throw a baseball or, a rock or something. So you might imagine I'll use those, a little pebble moving through empty space, right? You can do that if you want to. So an electron is like a chunk of something moving through emptiness. You can do that if you want to. It turns out the much more fundamental way and accurate way to describe everything in the universe is not like a little electron moving through nothingness, but instead the most fundamental objects in the universe are these things called quantum fields that permeate everywhere, all of space, everywhere, all the time. And then an electron is a little excitation in this field that we measure as a little thing going through space. So imagine you're like playing with your cat on your bed and you pull the sheet tight and you put your finger underneath the sheet and you move it around and your cat chases this thing, right? It's like, where's the thing going, right? But if you take the sheet away and you put your finger there and move it around, your cat's just like, what are you doing? Yeah, what are you doing? I'm going to the other room. So the thing did not exist unless the field was there, unless the sheet was there. It's the same thing with physics. So it turns out that everything in the universe is made fundamentally of these things called quantum fields. If that's the case, then the field is everywhere. And the problem, though, is that, and so I can have an electron, moving through one of these fields, but the place where there's not an electron, what is that? Is it nothingness? It turns out it is nothingness, but from quantum mechanical perspective, nothingness is in fact a field. And if I were to zoom in small enough, quantum mechanics says that there's no way for nothing to be completely stationary. In fact, it also has to fluctuate. And that's really weird. That's really hard to wrap our brains around. If I were to somehow zoom into the fabric of space, I would see these fluctuations. I would see like things moving around constantly. But that's what the case would be.
So it's like a bit fluctuating nothingness.
Constantly.
Yeah?
Everything in the universe basically vibrates and fluctuates all the time at the smallest possible scales.
Therefore, it a wave? We had a discussion yesterday with Marcel about waves. Is it a wave? Can you describe it as a never-ending wave?
You can, except you have to use the equations of wave mechanics, except you have to describe them, you have to use them in a very special way so that you're not talking about like a wave going through space. That would be more like a gravitational wave. But from a quantum mechanical perspective, the very smallest possible level, the smallest possible scales, you do use wave equations, except they're more kind of localized waves, if that makes sense. It's hard to kind of wrap your brains around if you haven't done a little bit of quantum mechanics, but you don't need to do that really to get a sense of it. Imagine instead of an electron, like I said, being a chunk of something moving through space, an electron is a little localized wave packet. So you can visualize something like this. Imagine, make it very simple, not a three-dimensional spatial wave, but instead think about it like a single line. Like if I had a chalkboard here, I draw a line, and that line is everything that exists. And so that if I have the line and then suddenly it starts to go, goes down again, this is a so-called localized wave packet. And I can describe that too. I have mathematics that does that. It's a wave that starts from zero, and then it starts to oscillate a bit, and then it goes back to zero. So that thing, in fact, can be the electron. And you can describe that with wave equations. Yes, you can. So yes, these are waves. But because the fluctuation, just to finish the thought, to get back to the point we were making, is that because everything in the universe at the smallest possible scale is vibrating and fluctuating, these quantum mechanical fluctuations, this means that inherent to the very fabric of space itself, the background fabric of space in the universe, there must be some kind of pressure, right? There must be something going on.
Heartbeat.
And if you take the entire universe as a whole, right, not just the little part around me, but everything, and you do the calculation, there should be a lot of this vibration that is moving the fabric of space itself. And in fact, it could be pushing the fabric of space outward. Okay, so you might think, oh, eureka, we found our answer. This is the answer as to where the accelerated expansion of space comes from. It turns out that that's absolutely impossible because there's an enormous discrepancy between what this fluctuation, we call it the vacuum energy of the universe. There's this, we call it the vacuum, right? Because from a broader perspective, if we just look out from our human perspective, we look out into space, an empty spot in space, there's nothing there, so it's a vacuum. But if I were to have my special, quantum mechanical device, I could look and see that there's a little bit of a vacuum fluctuation going on there. That vacuum energy is predicted to be way, way higher than it actually is observed. And this is like it's catastrophically wrong, like hundreds of orders of magnitude wrong, or 60 to 122. This discrepancy is one of the biggest, crazy, weird things that don't have an explanation for right now. So it's too much.
For us, it's nothingness, but in fact, it's super dense nothingness.
It is, yes. Nothing is never actually just nothing.
So the nature cannot stand nothingness. It always tries to put something in.
Correct. Well, not even that it tries. It's just that's just the way it is.
And now come back when you know the answer.
Yeah. No. It'll be an ongoing question for a very long time. And it gets a little bit complexified, if you will, because. So we know that we know the things that we can observe, and we have calculations and predictions, and then we have things that we observe and match those up and see how, and then we adapt the predictions and with new theoretical ideas, mathematical ideas that come in. And the funny part is that we know some very key things about our universe, but there's still things that are open-ended at the moment. The current best understanding that we have, like I said, is that the universe will probably end in this kind of heat death, if you will, this sort of empty soup of nothingness. But some other people have thought about, which you may have read about, which I find very fascinating. Quantum mechanics, the thing that I said about quantum mechanics, again, anytime we talk about quantum mechanics, quantum field theory, you have to remember that the rules of quantum mechanics are extremely different from the rules that you and I evolved as,
And we have no
evolved
idea
in.
why.
Well, why is, maybe not the right question. How it works, we understand these quite well. It's just, we can measure things about quantum mechanics, but the rules of what happens in quantum mechanics are very so-called counterintuitive to humans. It kind of makes sense, right? Because, you and I as a species, we evolved on this very friendly planet and this very, very narrow energy band and this nice distance away from this very friendly sun and just the right conditions so that we can eventually evolve and, have this conversation and drink tea and talk about the universe itself, right? That is, most of the universe is not like that at all. And especially when you get down to the smallest possible scale, quantum mechanics, the rules of what goes on there, which we can calculate and measure and predict quite well, they're very different from the rules that you and I engage in. So for example, right now sitting around here, there's basically zero probability that I will suddenly be measured as existing underneath the floor. But in the quantum mechanical world, this happens all the time. Like I can have a physical barrier and I can put an electron, a single electron, one side of the barrier. There is a certain percentage of the time, and then I stop looking at it and I look again. Most of the time it'll be on this side of the barrier, but some of the time, predictably, it'll be on the other side of the barrier.
So it teleports.
Well, it's so-called tunneling, quantum tunneling. It's just measured on the other side. Like this would never happen for you and me. This happens all the time in the quantum world. The reason I mention it is because all of this stuff we talk about, these quantum fluctuations, we talk about the vacuum energy of the universe having this kind of fluctuation power to it. It means that on long enough timescales, and again, we're talking about, the heat death of the universe, 10 to the power 1,000 years, 10 to the power, 1,000,000 years from now, these numbers that don't mean anything really to humans. On long enough timescales, certain things have to happen because quantum mechanics says they're allowed. And I don't know if that makes sense, but let me explain. So like I said, right now, there's basically a zero probability that I will suddenly tunnel through my entire body. Everything here will tunnel through the floor and go into the apartment below.
I hope so.
I hope so too. For my safety, I think that would be a good thing that doesn't happen. But the key phrase that I use there, the key word that I use there is there's a basically zero probability. In fact, there is a non-zero probability that can occur. And in fact, because there's a non-zero probability for all of my particles to just somehow conspire to do this all at the same time, if I wait long enough, if I were to sit here long enough, this would happen. It would have to happen. It's necessary from the equations of quantum mechanics. This has to happen. So if that's the case, on a long enough time scale in our universe, some theorists think about this, some physicists have thought about this, on a long enough time scale, the heat death might not actually be a heat death because on long enough time scales, something has to fluctuate in the quantum mechanical vacuum that would be structure, that would be somehow entropy going in the wrong direction, which is super weird if you think about it. So this is, some people may have heard of this as the concept of the Boltzmann brain. This was a thought experiment that, you can calculate how long would it take for the probability that just out of the vacuum, out of the quantum mechanical vacuum in space, suddenly a bunch of particles would just conspire, and they have to fluctuate this way to just have a brain appear out of nowhere. It might seem strange, but that's, statistically this has to happen. Quantum mechanics is a statistical, probabilistic theory, and we know that it's true. So eventually this must happen. So, far enough into the future, it's possible that just a brain will appear out of nowhere.
And what will it do? I mean, like sad, lonely brain sitting somewhere,
Yep.
I don't know, floating through the universe, and he's like,
Yep.
who created me?
Yep.
Is there a God out there?
Well, if it was a human brain, then yes, he would have the human tendency to start thinking in terms of theological explanations for things, which is, it's not really, we don't need these explanations anymore, but people still use them for some reason. Anyway, they must satisfy some kind of emotional need for people. But it's true. Like, what would you do? That's partially what I mentioned is like, I think that when I was talking about earlier, for me, the concept of the heat death of the universe, or the far enough future, if you go far enough into the future, right, when, if you think about it, the expansion of the universe is going to keep speeding up faster and faster, so that even right here, even if the Earth survives as an object, and say the solar system survives as an object, or let's say our galaxy survives as an object, we know that far enough into the future, even the galaxies that we see in space, the ones that make up the constellations and the things we can see, those will be moving so fast, so quickly away from us that light from them can never get to us anymore. So the entire sky would be completely empty and dark, except for maybe the stars from our galaxy. And that to me would be like, I mean, that sounds scary, but that would be fascinating. Imagine, it's like the ultimate, imagine if you had time travel, we could travel in the future. People ask, where would you choose to go? It's like, I might go far enough so that I could actually be in the universe where you couldn't see anything at all. And just kind of like sit there in the space. It'd be like the ultimate sensory deprivation chamber, right? Because like, it would be incredible. You know, you imagine going to the heat death of the universe, it'd be kind of the same thing.
And you're sitting like no ambulances, silence, nobody's like crying
Yep.
or knocking at your door, finally.
Yeah, the guy next door is not playing loud techno at 4 a.m.
Yes.
You know, it's just...
Yes. A paradise of an introvert.
Yeah, you know, I would also probably get pretty freaked out after a few minutes and want to come back, which is kind of a shame because I don't think we can do backwards time travel, but, you know, who knows?